All right, this lesson here, we're going to talk about theoretical and experimental probabilities. Okay, so we talked already that probability is the ratio of desired outcome divided by total number of outcomes. Okay, theoretical probability assumes that each outcome has the same chance of occurring, sort of. Okay, it's based on uniform probability. So what should happen when you are doing an experiment? If you flip a coin, what should happen is half the time it should come up heads and half the time it should come up tails. Experimental probability is based on the actual results of doing the event. Okay, it's also called sometimes relative frequency. Okay, the relative frequency of how often something actually happens when you are doing a specific event. Okay, so we'll take a look at some examples here. So in an experimental probability, you have to actually do things. You have to do the trials. You have to experiment and actually do the events and then see what the results are, as opposed to just looking at the situation and assuming that the events will come out the way they're supposed to. Okay, so I'll be more clear with an example here. So here is, first, there's an experiment. So here's a spinner, okay, has three. So it flips around like this and it lands on green 21 times, 15 times on blue, and 24 times on red, okay, out of 60 occurrences. So the graph tells you that the probability of getting a red based on the results is 24 times out of 60 spins. 24 out of 60 simplifies to 2 out of 5. They're both divisible by 12. 2 out of 5. That's the experimental probability of getting a red on the spinner. But it's pretty easy to tell what the theoretical probability is of this spinner, as long as the spinner is evenly, balanced. How many times should you get red out of 60 times? Well, 1/3 of the circle is red, 1/3 of the spinner. So 20 times out of 60 is the theoretical probability, or 1 out of 3. Okay, because there are equally sized sections. Okay, so experimental probability is based on actual experiments. Theoretical probability based on what should happen. Okay, now there's not really a reason to use experimental probability to make predictions. Okay, when you're going to calculate with something like this, instead you would just use the theoretical probability. All right, unless you were trying to figure out if this really had the same chances of ending up on each color of the wheel. Okay, if you weren't sure if this wheel was balanced or not, you spin the spinner a whole bunch of times and you get results that are not 1/3 red, 1/3 green, 1/3 blue. That would tell you maybe something is wrong with the spinner. So that's one reason why you would do the experiment. Okay, well, here's a better. So let's see. Let's continue on first. So the okay, so an example one. So let's say the spinner was spun 3 more times and it landed on green each time. So now what's the experimental probability of green? Well, 3 more times means you've now spun this wheel 63 times, right? Because you added 3 more greens. So plus 3 here in green means the total now is 63 trials, 63 experiments, okay? And it's now 24 out of 63. Okay, it was 21 out of 60, and now it's 24 out of 63. Okay, so what is this new theoretical or new experimental probability? Well, 24 and 63 are both divisible by 3, and you get 8 and 21. 8 21s. 8 out of 21. How does that compare with the theoretical probability? What's the theoretical probability of green? 1 out of 3. Okay, 8 out of 21, is that more or less than 1 out of 3? Well, 8 out of 24 would be 1 out of 3. So this is higher probability of green, right? Kind of get that more, especially if you got 3 greens in a row like that. All right, but a better question than this one is, let's say you spun the spinner 1,000 times and the results came up to this: 450, 275 red, and 275 blue. Okay, so if you spun it 1,000 times, what are the experimental probabilities now? 275 out of 1,000 is 450 out of 1,000 is 45%. That'd be 45 out of 100. 27.5% red and 27.5% blue, right? So if you did it 1,000 times and you got these experimental results, what would a possible explanation be? Why would it come up so many more times on green than on red and blue? Well, it could be that there was some problem with the spinner. Maybe there was some friction here that made it stop on green more often. Okay, something that made it not random, that you didn't have the same chance of landing in all three spaces just because the sizes of the spaces were the same on the spinner. Okay, this is important if you were designing something or playing a game, right, where you realize that, hey, every time I spin the spinner, it comes up on a 9 or 10 instead of these other things. Maybe something's wrong with your spinner, right? All right, let's do a little more interesting experiment here. And we're going to start with the marbles in a bag is what it says here. I actually have 12-sided dice in this green cup, okay? And I'm going to pull a marble from the bag and I'm going to put it back in, okay? So I'm pulling out and it's purple, okay? So I get a purple, put it back in. And pulling out again, and this time it's green, okay? So green. And I'm going to do it again, and this time it's red. Okay, so I do this 50 times, pulling marbles out of this cup. I don't know how many of each type are in the cup, okay, but I do it 50 times, and these are the results that you get. 14 times it comes out red, 19 green, 8 purple, and 9 blue, okay? So what are I can't do any theoretical probabilities here. I don't know how many things are in there, so I can't do that. I can just do the experimental times. Out of 50 times, these are the results that I got. So what's the probability as a simplified fraction and as a percent? Okay, so simplified fraction, 14 out of 50. Okay, these are easy to convert to percents, right? Because if it's out of 50, to convert to a percent, you just have to make this bottom 100, right? So it's going to be twice as much. Out of 100 times, you would expect 28 reds. So that's 28%. Simplified fraction, 7/25. Green is 19 out of 50, or 38%, right? 2 times 19, 38 out of 100. Purple, 8 out of 50. That simplifies to 4 out of 25, 16%, twice 2 times 8. And blue also is 9 out of 50. That doesn't simplify at all, and that's 18%. So here's your results. 28% of the time you got a red, 38% of green, 16% of purple, 18% of blue, okay? If there's 20 marbles in the bag, if there are 20, I tell you there's 20 dice, right? 20 marbles in the bag, 20 dice in the cup. What's your best guess of how many of each there are, okay? If you had to split this out into 20, well, what do you think? Want to try to get these out of 20 instead of out of 100. So you could divide each of these numbers by 5, basically. Okay, kind of round them off. But you would basically divide each one by 5, each percent. Okay, so this one's going to be 28 divided by 5 is somewhere between 5 and 6, right? 5 or 6. This one is going to be 7 or 8 greens, right? The purple, 16% is about 3 then, and 18%, 3 or 4, okay? And you could tweak these a little bit, right? You only did it 50 times. Maybe this is 7 and this is 3, okay? But this is a good guess based on the experiment that you did, okay? You think, oh, there's 6 red, 7 green, 3 purples, and 4 blues. That's the best guess of what's in the can. And you just keep pulling out marbles, maybe you get a little better guess, right? If there's 20 marbles in the bag, Okay, your guess is this: 6 red, 7 green, 3 purple, 4 blue. What could you do to get a better estimate of how many of each color there are in the cup? What would you do? Well, yeah, you roll a bunch more times. If you roll, so say you picked out, not roll, but picked a marble out again 100 times. You pick 100 marbles out, you get these results. Very easy to do the percents, right? 34, 37, 15, and 14%. You get these results. Again, still experimental probability, all right? Well, how could you get, would you change your guess then? Would you change the numbers here of how many you think there are of each one? Well, now maybe you would say there were 7 reds and maybe 7 greens and 3 of these and 3 of these, right? Maybe that's your count now. Instead of 6 red and 4 blue, you just tweak your numbers a little bit to match, because these percents, the more you pull out of the cup, the better your experimental result is going to be, the closer it's going to be to the actual results that are in the cup. You did it 1,000 or 500 times, okay? 500 more times. So you're just pulling the marble out 500 times, and you get these results. Would you change your answers? Here's the percentages that you get. 173 divided by 500 is 35%. Now, well, there's no question now, if there's 20 marbles or dice in the bucket, it's 7, 7, 3, and 3, right? That's how the percents work out. And it turns out that that's what I did have in this cup, okay? So if we wanted to, we could pull out of there 500 times, 1,000 times, and you get close to percentages that matched up, okay? Now, this kind of thing is useful to predict what's going to happen in the future. If you know out of a certain amount of an experiment how often something happens, then you can use a proportion, which we've learned how to do. Use a proportion to make predictions about the future. Very important use of probability. It's one of the most important things that you do with probability. So last year, a DVD store sold 670 action DVDs, 580 comedy, 450 drama, and 300 horror. Okay? A guy expects to sell, this is an old book, right? Expects to sell 5,000 DVDs this year. Well, based on these results, how many comedy DVDs should she buy? Okay, well, we need to know how many they sold here in last year. We need to know the total, right? Because the number of comedy DVDs out of the total would give us your probability of selling a comedy DVD. So that's 580, the comedy, okay, divided by 2,000. 2,000 comes from 580 plus 670 plus 450 plus 300, right? They didn't tell you that there were what the total was, okay? So you have to add it up yourself, and this comes out to 2,000, right? So 580 out of 2,000 were comedy DVDs before. I mean, you could simplify this if you want to, although there's really no reason to if you're going to use a calculator, okay? So now we set up a proportion, right? Comedy, just like we did back in Unit 4. Comedy over total equals comedy over total. And now our total is 5,000 instead of 2,000, which we could put here, okay, or 100, the way they did it there. Okay, and we can cross multiply. Remind you over here how to cross multiply, right? 29 times 5,000 and 100x. Then you divide both sides by x, and you get 1,450. So the prediction is, if you're going to sell 5,000 DVDs, that 1,450 of them will be comedy DVDs. And this should look very familiar to what we did back in Unit 4, doing proportions. All right, so let's do these last couple questions here on the guided practice, and then we'll have another discussion in class. Okay, a coin is tossed 50 times. A coin, heads and tails, right? So it's going to land either heads half the time and tails half the time, right? That's the theoretical probability of landing on heads, okay? The theoretical probability, that is 50% or 1 out of 2, okay? The coin is tossed 50 times and it lands on heads 28 times. What's the experimental probability? The experimental probability is what comes out of the experiment, what you actually did. 28 out of 50, 28 out of 50. The experimental probability, 28 out of 50, which is 56%, okay? Multiply this by 2 to get a percent, or divide in your calculator, and then you get 0.56 and move the decimal place, percent, fraction, and decimal conversions. Okay, as a simplified fraction, this is 14/25. 14 out of 25, or, okay, so the experimental probability, 14 out of 25, 56%, higher than what you would expect in the theoretical probability. What does that mean? Nothing. It just means you need to toss the coin more times, okay? Because if you toss the coin, a coin doesn't really have any way to be unbalanced, I don't think, okay? All right, next one. Yesterday, this one's better experimental probability problem. Yesterday, 50 bakery customers bought muffins, and 11 of them bought banana muffins, okay? So 50 total, looking for the total number of outcomes. And this is the desired is 11, okay? So how many, if you had 100 customers tomorrow, how many banana muffins would you expect to sell? This one's pretty simple numbers, okay? So it was 11 out of 50 today, and tomorrow, out of 100, how many would you expect to buy banana muffins? Okay, this one you can do in your head with equivalent fractions. It's 11 out of 50, well, twice as many people, you would expect twice as many banana muffins. So your answer is 22 people. Okay, so experimental probability is really just doing things, doing a trial, testing something out, and counting how many times something happens out of the total number of times. Okay, and then the result of that is your experimental probability. Theoretical probability is what should happen, okay? And with the more appropriate use of experimental probability is when you don't have a theoretical probability. Like, there's no way in theory you could figure out what percent of people would pick banana muffins. You have to just track what they buy, okay? As opposed to flipping a coin, where the theoretical result is very simple, okay? Or rolling a die, right? So if I use this die here, this is an 8-sided die, actually a 10-sided die, okay? And if I roll this, I would expect 1 time out of every 10 to get an 8. I would expect 1 time out of every 10 to get a 4, right? The probability of each result on this die is 1 out of 10, because there are 10 equally possible results, and if each number is the one we're looking for, right, in simple probability, your probability is 1 out of 10. Now, I could do the experiment and keep track of it, and we'll do some of this later on to talk more about experimental probability and theoretical probability. Okay.